This video will present the issue of corrosion in reinforced concrete and how to mitigate them using inhibitor technologies. There are many types of reinforced concrete structures, such as buildings, bridges, silos, etc. Reinforcing steel bars are added to the concrete to increase its tensile capacity. During its hydration process, cement contained in the concrete produces calcium hydroxide, which has high alkalinity. So we could say that reinforced concrete is acting like symbiosis in nature. On one side, the steel is providing the necessary tensile resistance, while on the other hand, the concrete is protecting the steel from corrosion. While this protective layer is maintained, the steel remains passive and free from corrosion. Steel has a tendency to revert back to its original state, iron oxide. This phenomenon is called corrosion. This is happening when the passivity of the steel is lost due to various reasons. Steel corrosion has severe implications in the economy. For example, in the USA alone, the cost of corrosion in highway bridges reaches more than $8 billion per year. Unfortunately, corrosion cost is not just economical. Recent disasters in Italy with the Genoa Bridge in 2019, and more recently in the US in 2021 at the Surfside condo collapse in Miami, have resulted in many casualties. High levels of corrosion are a contributory factor to the collapse of both structures. To efficiently prevent corrosion occurring, a better understanding of the reaction behind the corrosion process is needed. This corrosion is mainly due to two main causes: carbonation-induced corrosion and chloride-induced corrosion. Carbonation-induced corrosion is a naturally occurring phenomenon. In a previous slide, we mentioned that during the hydration process of the concrete, calcium hydroxide is being formed. This compound has a naturally high alkalinity with a pH around 12 to 13. However, when the carbon dioxide molecules present in the atmosphere penetrate the concrete, they react with the calcium hydroxide and produce calcium carbonate. This reaction is actually not negative to the concrete itself, but results in lowering the pH to around 8, and at this pH level, the passivity of the steel is lost. This is a slow process and may take years for the carbonation front to reach the level of the reinforcing bars, especially if the concrete quality is good and the concrete cover is high. When this carbonated concrete becomes wet during rain, the concrete conductivity is increased through low electrical resistivity of the water in the pores. A multitude of microcell corrosion forms rust uniformly on the depassivated rebar. The produced rust has a larger volume, creating heavy stress on the concrete cover, leading to cracking and delamination. The corrosion process in the reinforced concrete is similar to the process in a car battery. Corrosion occurs at the anodic zone and not at the cathodic zone. Here are a few examples of damages due to corrosion in various structures: buildings, bridge beams, car parks, etc. It can be noted that most structures presenting corrosion damage due to carbonation present very low concrete cover, as seen in the different photos presented. We can also see the overall uniform corrosion typical of carbonation-induced corrosion. Another root cause of corrosion in reinforced concrete is the penetration of chlorides in the concrete, reaching the reinforcing bar level. These chlorides can come, for example, from de-icing salts used in winter, or from salt water, amongst other sources. When chloride ions reach the rebar, a localized large anode is formed with the formation of hydrochloric acid that also lowers down the pH of the concrete to a very low level. This large anode is responsible for a typical corrosion due to chlorides, which is pitting corrosion. Here are two examples of typical chloride-induced corrosion. The one on the left being the underside of a bridge beam, most likely due to de-icing salts, and the one on the right, a pier in a port. We can note the pitting corrosion on the reinforcing bars in the picture on the left. We can clearly see the result of pitting corrosion in the two pictures on the right, showing a closer look at reinforcing steel bars corroded by chlorides. Actually, we can note some chloride salt deposit in the one in the bottom right. When dealing with damages due to corrosion, a full system approach is needed in order to repair the structure to its original state and to improve its durability. Depending on each situation, various systems of mitigation can be offered to the market, from basic repair management, protective coatings, strengthening when required, to corrosion management itself using either cathodic protection or corrosion inhibitors technologies. In the rest of the video, more information will be given on inhibitor technologies. Different systems of corrosion inhibitors are available. Amongst them, there are active and passive inhibitors. Surface-applied active inhibitors are applied at the concrete surface. Their active molecules do not react with the cement compound or the aggregate, but can migrate to the rebar level. These systems will only be effective if the active molecules can migrate through the concrete cover to reach the reinforcing bar level. In Sika, the first version of this inhibitor was introduced in the late 1990s. We are now in the third generation of this technology, and millions of square meters of concrete surface have been protected since then in all continents. The passive systems are acting differently by reducing the humidity at the reinforcing bar level. As a consequence, the resistivity of the surrounding concrete is increasing, reducing the corrosion rate. Using concentrate silane passive inhibitor, another big advantage is achieved, that of preventing further penetration of chlorides in the concrete. However, this technology can be used only at areas where the concrete is able to dry out, as the silane will prevent liquid water to penetrate the concrete, but allowing the water vapor to escape. If this is prevented somehow, they will not be able to perform as a corrosion inhibitor. These two silane compounds, Sikagard 705 and Sikagard 706 Thixo, were introduced by Sika in the mid-1990s. Studies and publications in the last 10 years have shown their ability to arrest corrosion in certain conditions, even when the corrosion is already active, like in the curve presented in the picture in the bottom right, and to prevent corrosion when the silane is applied on cracked concrete prior to the initiation of the corrosion, as shown in the curve presented in the picture in the top right. Both products comply with the highest requirement of EN 1504 Part 2, especially in relation to the control of resistivity. In summary, typically for carbonation-induced corrosion, we find low concrete cover, relatively low concrete quality, and slow corrosion speed. For all of these factors, due to the necessity to reach the reinforcing bars level, active inhibitors are very effective to deal with carbon-induced corrosion. They can be used alone or as additional protection underneath acrylic protective coatings. Typically, corrosion induced by chlorides are common at bridges, piers, and marine structures, where the concrete density and quality is higher than in general buildings and the concrete cover is also higher. Corrosion induced by chlorides is also much faster than for carbonation-induced corrosion. For all these reasons, if the structures are allowed to dry out, passive inhibitors are a viable and effective option. To conclude, the surface-applied corrosion inhibitors presented in this short video are part of the full total concrete refurbishment management concept in Sika. They can be a cost-effective and sustainable solution in certain conditions. The selection of the inhibitor types can be summarized as follows. For carbonated concrete, active inhibitors such as Sika Ferrogard 903 Plus can be used alone or combined with SikaGuard protective coatings. For chloride contaminated concrete, when the concrete can dry out, passive inhibitors such as SikaGuard 705L or SikaGuard 706 Thixo can be used. And when the concrete cannot dry out, or if the corrosion is too advanced, then cathodic protection should be considered. Thank you for your attention.